Okay, thanks very much, James. So, good morning, everyone. So I'm now going to talk a little bit about climate change and flood risk. Excuse me, and I'm going to start by just rewinding a little bit. Jane's given us a very detailed account of some of the things that we've learnt from the flooding that occurred during this past winter. I want to just rewind slightly to 2 years ago to January 2014. During that period, we were in the midst of severe flooding and quite prolonged flooding over large parts of the south of England in particular, specifically in the Thames catchment. At this time, the Prime Minister, David Cameron, stood up and said essentially that he thought that those floods that we were experiencing were probably connected to climate change. He suspected they were probably linked to climate change. And of course, this begs a scientific question. You know, what's the evidence to support that statement? And when David Cameron said this, I thought, well, we've been here before, haven't we? Because rewinding even a little bit further back, this is the then Deputy Prime Minister John Prescott up to his knees in it on the BBC website in November 2000, when of course we also experienced prolonged and widespread flooding across many parts of the country. And at that time, John Prescott also said that he suspected that the flooding was in some way connected to global warming. When he said this, the Department of Environment quite reasonably thought, well, hang on a minute, let's work out what the evidence for this kind of statement is. And as a result of that, asking that question, they commissioned some research work carried out by quite a large team of scientists from the Met Office and the Centre for Ecology and Hydrology, so that's the country's national research institute for hydrological science. I was working there at the time before I joined JBA and led the team that wrote that study. And of course, one of the great difficulties in analysing, looking for a climate change fingerprint in flood events is that it's very difficult, and any hydrologist will know this, it's very difficult to identify really compelling, clear-cut evidence of trends in historical records of flow data. So looking at the Thames catchment in particular, this is the catchment boundary for the River Thames, and throughout this talk I'm going to be referring to the Thames as it drains down to Teddington Weir. So Teddington Weir is the point at which there's effectively a separation between the tidal Thames and the fluvial River Thames. So if you like, it's the point at which the river turns into an estuary. So we're looking here at a time series, a plot of the annual maximum, so the largest flows recorded at Teddington Weir historically. And the Thames is a really interesting catchment from a science point of view because it has one of the longest high-quality historical records of river flows anywhere in the world, really, so going right the way back into the 19th century. And what you can see on the graph here are sort of two kind of standard approaches to trying to fit some kind of trend line through that data. So one's a linear trend, one is a smoothed estimator. And okay, you know, there's maybe some hint, some suggestion of an upward trend there, but that's somewhat confounded by the fact that some of the very largest flood events historically have occurred even back into the 19th century and certainly early 20th century. So from this kind of analysis, it was very difficult to provide any kind of conclusive evidence to say, well, there's clear signs of some sort of climate change signal against this backdrop of very variable, you know, high degree of variability in those data. So we wrote this kind of result up. We followed all the latest government guidance on communicating scientific uncertainty. Our report was published, and the following day, The Times ran a piece on it that said, "Flooding baffles scientists," which isn't quite what we actually said, but in retrospect, I suppose I can see why they came up with that headline. And our comment really was to, you know, exactly as I've just explained, that we couldn't categorically provide any sort of attribution of that one flood event to climate change. So I'm going to fast forward again now and bring us back up to date and look at what we can say now. What we can say now, and this is with reference to the flooding in winter 13-14 in the Thames, is that actually there is evidence to say that historical climate change, so greenhouse gas emissions since the Industrial Revolution, has already put around about 1,000 properties at additional risk of flooding within the Thames River catchment. So remember, this isn't taking account of sea level rises or storm surges. We're just looking at the river catchments. So that's quite a strong statement. In relative terms, compared to the total number of properties in the Thames River Basin, of course, 1,000 is still a relatively small number. It's clearly not a small number if you're one of those affected properties. And there's a wide uncertainty range around this. So that estimate is bracketed between -4,000 and +8,000. So that does seem like quite a wide range. As I'll come on to show you, there's still a very strong message in here on the balance of probabilities that this is a fairly robust indicator that the increase in risk is real. There's also some small print. I'm not trying to be deliberately concealing here. I was hoping it might be just about legible at this scale. Maybe it isn't. But basically, that's there almost just to remind me to point out that all these types of scientific studies do have a set of assumptions behind them, and often actually they're quite difficult to explain and to digest. But here, essentially, the assumptions are that we have to have some confidence in the climate models that are being used in this analysis, which I'll explain about in a minute. But there is quite a lot of evidence and investigation behind those to suggest that they're reliable. And we have to make a few assumptions in there about the way in which we count property damages and so on, which again I'll explain about. So what I'm going to do now is just briefly summarize the analysis behind that headline result of 1,000 properties at additional risk due to climate change. And really what I'm doing here is summarizing results that were published in February this year in a journal paper in Nature Climate Change. This is a study that was led by the Environmental Change Institute at Oxford University. So the lead author here was Natalie Schaller, postdoctoral researcher there, with input from the Centre for Ecology and Hydrology that we've mentioned a number of times, myself and a colleague, Jess Skeggs. So I was involved in this through the JBA Trust, which is our not-for-profit research foundation, and working with Jess in JBA Risk Management to use our flood mapping data. And there were a number of other institutions involved in this study, so you can see them listed there, including the Met Office. And the starting point here was to look at what was actually happening during the winter of 2013-14. So here we have a graph showing historical series of rainfall. This is rainfall recorded at Oxford. Again, an exceptionally long, high-quality data series going way back into the 19th century and beyond. This plot shows each of these bars is the January rainfall recorded at Oxford. Here's the January 2014 data, which clearly sits right at the extreme end there. It was a record-breaking extreme rainfall. And you can see plotted in here also a type of trend analysis, which again, as with the river flows in London at Teddington Weir, maybe there's some sort of hint of slight increases there, but there's a lot of variability as well. And it's difficult to sort of identify a conclusive definitive trend in there. There's also perhaps a slight suggestion if you kind of look at the density of these bars. So in the earlier period of the record, quite a few of the Januaries there were below the long-term average. As we move into the later part of the record, more and more of these blue bars appear where January was above the long-term average. So perhaps there's a slight shift indicated there towards more extreme rainfall. But certainly we're really interested in understanding what's going on during this exceptional event that we had two years ago. So that's the kind of local scale scientific data that we have, the measurements of rainfall from a gauge in Oxford. But we also, of course, now have really good information about what's going on at global scale. So what you're looking at here is a map of sea surface temperatures. Sea surface temperature is one of the critical parameters within the global climate system. And this is data that's produced from a range of observation networks and model interpretations. And this shows the difference, the anomaly, as climatologists would call it, between the sea surface temperatures that were observed during the winter of 2013-14, December, January, February, DJF, versus the long-term background values. So it's the deviations from the normal conditions. And what we see is this patch of blue here, which indicates colder than normal sea surface conditions over the North Atlantic, and then also some of these red patches around in the Caribbean, the Gulf, and elsewhere, indicating warmer than usual conditions. So somehow this kind of unusually cold North Atlantic was connected to the weather systems that ultimately led to the flooding we saw in southern England. So the analysis that was conducted by the research team here was then involved saying, well, okay, if we take this as indicative of what was going on during the winter of 2013-14, what might have happened, what could the weather have looked like if we then somehow subtracted out the influence of anthropogenic greenhouse gas emissions since the Industrial Revolution? And we can do that, we can answer that kind of question by looking at results from global climate models that have been run as a kind of numerical laboratory experiment in which the global climate is simulated with all the kind of historical greenhouse gas emissions included, and then a second simulation is performed in which the atmosphere has been held in its pre-industrial state. So we're kind of comparing the real world with model simulations of a counterfactual world in which we take out the effects of greenhouse gas emissions. And these plots, these are results from 11 global climate models produced by various different scientific research institutes around the world. So this is the Met Office model down here, showing the effect on sea surface temperature patterns over the winter period if we perform that experiment in which we subtract the effects of greenhouse gas emissions from the present-day real atmosphere. So we see these sort of changes in average sea surface temperature. And so what these maps are showing in effect at that global scale with respect to those sea surface temperatures is the effect of human greenhouse gas emissions or industrial greenhouse gas emissions on those average temperatures. So the question then is, what impact would that have on the weather? So those plots are of kind of long-term or seasonal average climate conditions. What we want to do is then connect those average conditions to actual weather events that might drive flooding. And this is where we made use of a very large scale computing experiment called climateprediction.net, which runs a model called Weather at Home. So this is an Oxford University initiative that essentially uses networks of home computers and their spare processing capacity to run thousands and thousands of climate and weather models in order to build up big ensemble simulations. And so what's been done here is to move from the kind of very coarse scale global model data. So you can see here these pixels, these boxes represent the large grid, coarse grid of the global models that we saw on the previous slide, and to convert those through into much higher resolution data. This is down to 50-kilometer grid scale that can start to resolve weather features in a more realistic way. And I should add here that this 50-kilometer scale is something that's being reduced all the time as these kind of models advance. So the team at Oxford kicked off a very large ensemble experiment in which they effectively used this weather at home modeling process to generate simulations of plausible, physically possible weather conditions that could have occurred both for the real sea surface temperatures, so this is ensemble A, that were experienced in winter 13-14, and then for all of these 11 sets of pre-industrial weather conditions. So these were experiments that gave simulations of the weather as it might have been without greenhouse gas emissions, without climate change. And in total, there was something like 135,000 simulations of winter weather produced during this experiment. So that number and those ensembles are really important because they're a way of allowing us to perform an analysis that incorporates a realistic view of the uncertainty in the data and the uncertainty in the models. Every single one of those 135,000 simulations has got tiny little perturbations in it that represent that uncertainty. So we're not just we're not just looking at one model prediction that could be wrong. We're looking at a huge range of, if you like, replications of an experiment to account for the experimental uncertainty. And so what do the results show? Well, as I said, each ensemble experiment is in effect a simulation of what the weather might have looked like with and without climate change included. And those thousands of simulations, of course, produce weather events that range in severity from very severe to less severe. And we can extract all of those weather events from each of the simulations and look at their probabilities within each of those ensembles and express the probability also in terms of a return period. And therefore generate curves that look like this. So this result is for January mean precipitation. So this is the thing that was really extreme in January 2014. It was the 30-day average rainfall that was really extreme. The red curve here shows results for the world as it is now, so for the actual real climate that we have now. And each of those blue curves then shows the equivalent results for one of those model ensembles in which we've removed the effects of climate change. And so the simple way to interpret this is to say that if we were to experience a weather event with a return period of 100 years, let's say, what we're seeing is that the January mean rainfall in the real world, as we have it now, is more severe at that return period than any of those, or virtually all of those simulations for a world with a pre-industrial climate. Also put it another way, the effect of the climate change, of the greenhouse gas emissions since the Industrial Revolution has been to increase our expectation about that kind of extreme January rainfall. So in other words, climate change is leading to an increased risk of this type of extreme rainfall. So those kind of results have been produced for the weather, for the rainfall itself. And as I said, each one of the dots on that curve in effect corresponds to a simulation of weather over the full 6-month winter period. Each of those simulations was then fed into a hydrological model. So this is a model produced by the Centre for Ecology and Hydrology. It's been widely used and validated for various research studies into flooding. And what it does is it predicts the river flow down here at Teddington Weir, given a series of rainfall inputs. And so from the results of those hydrological simulations, the team produced the same kind of analysis of the risk of extreme river flows in this case. So again, this is looking at the total river flow over a month, over a 30-day period. In the paper, you'll see there's also similar analysis for other time periods going right the way down to the daily scale. And again, what we're seeing is that for simulations in which the effect of climate change, of human climate change, has been removed, so that's all the blue dots, the extreme river flow that we would expect is in general less than what was actually observed, what would actually be observed in the real climate as we have it under the actual atmospheric conditions that we have today. With one or two exceptions. So there are a few of the blue lines that are above the red line there. So again, pretty clear message about an increasing risk of extreme river flows associated with historical greenhouse gas emissions. The final stage of the analysis then was to try to link that type of understanding of impacts on the natural system into the implications for flood risk in terms of properties affected by flooding. And this is where we used the JBA risk management flood maps. So here's an example. This is the 1 in 100 year flood outline on the main River Thames. And by analysing properties included within our flood maps using property level data, so it's Ordnance Survey address point data, we're able to produce a very, I mean, this is, it really is a very simple impact model here, relating the return period of an event at Teddington Weir to the number of properties potentially affected by flooding, and there's a little bit of extrapolation on that curve as well. Just to provide a bit of ground truthing, there's an independent estimate that we can compare with here, which is the data from the Environment Agency's Catchment Flood Management Plan for the Thames. So that's the green dot there. So we think that we're kind of in the right sort of place on the graph here. We had to do this in a very simple way because the model analysis that was produced here only gave us predictions of river flows at Teddington Weir rather than throughout the catchments. If we were doing this sort of analysis again, or doing it in terms of the kind of thing we would provide for the industry, we'd do this in a rather more sophisticated way. But this is already, we think, good enough to give a first indication. And when we take that property analysis through and combine it with the results from the climate model ensemble simulations, what we get is a result that looks like this. So what's plotted here is the increase or decrease in the number of properties that we think are at risk for each of those ensemble climate model experiments. 0 would be no change, so 0 in effect corresponds to today's climate. Each of the blue lines represents one of the ensembles, and the thick blue line in the middle here represents the average of all the ensembles. And what this is showing us is that if you fit a straight line through that blue wiggly line, that comes out at approximately 1,000 properties placed at additional risk of flooding because of the climate change signals since the Industrial Revolution. The large uncertainty bounds that I quoted earlier come from the range in those ensembles, and they are wide, but one thing to note is that more of the ensemble results sit in the upper half of this graph. Okay, so there's more, on the balance of probabilities, we're reasonably confident that this increase in numbers of properties at risk is a robust result from that modelling work. So I just want to finish here with a couple of headline messages just to summarise what we found here. The study that's been conducted here has in effect been designed to isolate the impacts of climate change, of greenhouse gas emissions on flood risk. Just taking that one factor out and leaving everything else as it is. And it's still a relatively new type of analysis, but it allows us really to focus in on the implications of climate change and to do that in a way that sees through all the variability and noise in weather patterns and weather systems that makes trend analysis very difficult. From that analysis, we can make a reasonably confident statement that for a winter like 2013-14, we can already see this increase in risk that can be attributed to human climate change. That's still a relatively small increase with relatively wide uncertainty, but it's the balance of probabilities weighs strongly towards that conclusion. And I suppose in a way it's an early sign that we're already seeing evidence of the effects of climate change on flood risk, certainly for southern England, winter flooding. What I haven't shown you here, because there's no time, but is explained in detail in the science paper, is that there's some really plausible physical drivers for these changes. So this isn't, in a sense, just a kind of numbers game with a load of computer models. There's some quite kind of clear physical understanding of the physics of the atmosphere and the way that weather systems develop that sort of backs up and helps to validate these kind of results. And just a comment, I'm talking here about winter 13-14 because That's what we've got published results for, and it does take a year or two for these kind of studies to work through the peer review system before they're published. But early analysis by the same research team, just looking at the weather events, the rainfall from last winter, has also produced similar findings about the fingerprints of climate change being visible within those weather events as well. So this would appear to be a fairly general finding. Just a final comment then, there is more information available on the JBA Trust website at this URL. We produced a short commentary that gives a slightly less technical explanation of what the paper did and what the results mean. And there's further information on the climateprediction.net website about those studies looking at the rainfall events last winter as well as winter 2013-14. Okay, so I'll finish there. Thank you.